Welcome everybody to the I2DL lecture. This is the third lecture and we will continue today by introducing neural networks. However, before going into neural networks, we would like to follow up quickly what we have done in the last lecture and continue setting in respective context and then developing how we use those for neural networks. So if we're continuing from the previous lecture, the big thing what we have learned now is how can we set up parametric models, how can we set up a thing such as linear regression in order to perform supervised learning. And the core idea there was essentially that we have a parametric model. This is our function, right? And this function here is parameterized by theta. Theta is a vector that has a bunch of components. Number of components is d plus 1 here. And what we would like to do is we would like to find a model that is parameterized by that function that explains a target given a respective input. So in other words, we want to fit this hyperplane in this case. We want to fit this to our data points. And when we're feeding in x, we want to make sure that our model here explains y to the best of its ability. And the point of the training figuring out is essentially what these parameters theta are, right? And in this case, of course, if this is in, it depends on the dimensionality here, like how many inputs we have. Depending on the input features, we will then have a specific number of parameters in our linear regression. And we will have one more parameter. This is our theta 0. This is our bias. And we're going to call this term bias later on also in neural network land. And then the whole idea is that we give them a bunch of training samples, meaning that we have XY pairs, these orange dots here. We would like to find the optimal parameters theta, such that this line or hyperplane here can be fit to the best of its ability to these points. And what does best of its ability mean? Well, there's going to be certain loss functions. We're going to talk about some of these ones today. We have seen the L2 loss function, the mean squared loss, and that was, in a sense, the target we would like to have in our optimization. And then we would like to optimize it. And based on the optimization as an output, we're going to get our nice hyperplane. We've also talked about the logistic regression. For the logistic regression, we have a loss function that looks something like this here. And the idea here is that the y's here are the respective ground truth labels. So y is either 0 or is either 1, right? So this is the term that is non-zero when we have a positive label. This is the term that is non-zero when we have a negative label. And y hat here is our sigmoid xi times theta. So this is the linear part here, and we have a sigmoid function around it that squashes the logistic regression between 0 and 1. So we can kind of interpret it as a, it's kind of a probability. And then what we're doing here in our total cost, we are simply summing up the cost is the sum now over the loss over every single sample, right? So we're going here from I equal to 1 to n. We're summing up all of our losses here. And then what we're doing is we're minimizing this term here. And we're trying to make sure that we get as close as 0 as possible, meaning we want to make the cost as small as we can. Okay, and yeah, the optimization, of course, goes over theta. Where does the thetas come into play? Well, the thetas are here as part of our linear weights that we are multiplying with the respective xi's here. Okay, so if we're comparing the logistic regression against the linear regression, we haven't talked too much about it in the previous lecture, but the core intuition behind that is if you're having a linear regression here, we're having always this linear line, right? We have a bunch of samples here, we have a bunch of samples here, but we're going to have this problem that, this is kind of extrapolating. So when x is going further towards the right here, we would still try to extrapolate in a bad way. For instance, if we're doing a classification. And if we are having a sigmoid function, then we're going to get something like this, right? So here we make sure that we don't have the outliers here that would kill our classification, right? And this is kind of nice when we do classification. So logistic regression is kind of the right way to do here. So these were the two differences that we saw here. And both of these things are widely used machine learning methods. And if you want to solve a simple toy problem. We've seen a bunch of them in the last lecture. These things can actually get you pretty far. So you don't always need a neural network. These ones are relatively easy to do. And they can be actually applied, as I said, to a wide range of problems. So then what we talked a little bit about was how do we obtain these models, right? So the idea is now we have this concept of learning. And this concept of learning means that we have some data points. These data points, they give us some model parameters. They give us an estimate. We're comparing this estimate with our ground truth labels. We're having this loss function that we just had. And then we kind of iteratively update our model parameters by using an optimization. Of course, this is very high level. In practice, this is very mathematically defined, right? What we have is for instance, an L2 loss here. Based on this L2 loss, we know exactly if we're adding a certain sample, we know how wrong the sample is in the respective model prediction, and based on that, we can compute later on gradients and then update the model parameters. But this is going to come later today, and in the next lecture, how exactly we're going to do this for the model. And this model can not only then be applied to linear logistic regressions, what we've seen today, but this can actually, in fact, also be applied to neural networks. Okay, so if we are summarizing this, so far what we have had is we had these linear score functions, right? So in the linear regression, what we had is we simply had a function here, fi, right? We have here a bunch of weights. These were our thetas, and we're going to call the thetas now w's because w's is what we're going to use in the neural network land. And we're multiplying them with the respective x input, which is the features of our respective data, right? And we're going over all of these depending on the dimensionality of the input data. And based on that, we're going to get a function value here. This is our score. And this score value is determining what the respective response of that function to these samples is, right? So for linear regression, that tells us, for instance, we have some input parameters for the weather, right? And then the output would be the weather value. We typically going to write these ones as matrix notations because that's just a lot easier, right? Because we don't want to have the sum all the time. So we just have w times x is equal to our function value. And now what we can do here is we can say, if we have such a linear score function and, for instance, we would like to apply this for image classification, we could do the same thing for image classification. And the way you would do this is you say, we're having here x is going to be an image as input. F is our score for the respective class, meaning that if you have a higher score here, that it's more likely that this is the right class. And the W is our model that we would like to learn such that we're going to get high scores for the respective classes that we believe are corresponding to the ground truth labels. Right? So in other words, what we're doing right now is we're trying to figure out, give me X, which is an image. This is our input feature. What we would want to do is we want to multiply it with a certain model weight, and we want to figure out based on this multiplication what class it is at the end of the day. And if we're doing something like this on an image data set, you can actually do that. You're going to get results that look something like this. And this is a data set that is a relatively small, it's like tens of thousands of images, it's CIFAR 10. The idea of this data set is it's relatively straightforward. It's a very simple data set. It has only 10 classes. And each of these classes each of these images are relatively isolated, meaning that you have pretty much one object in the center of the image, and it doesn't have a lot of clutter and it's not that complicated. But if we are going ahead and taking the linear score function here right now, and we're trying to find the optimal set of weights, W, such that the score function should be high to match the respective class labels. And if we're doing that, and now we're visualizing the W's as images, so we're doing nothing else but visualizing the respective response function, so give me image as input, multiplying with the W's, so then we're getting a certain response, and now we're visualizing this function, so we're visualizing these W's as an image in itself. And if we're doing this, you're going to get results that look like these here. And this is actually kind of interesting, because what that means basically is, if I'm, for instance, fitting in this exact image, let's take this one here. Let's feed this image into this function here. So assuming I take x here as input, and if my x here corresponds exactly to the w, then obviously I'm going to get a pretty high value for f, right? So if my x here would not correspond to w and would be very different, then all these multiplications in this matrix vector multiplication here would be all 0, right? And this is the interesting thing right now. So if we had optimized for these w's based on the data, you actually are going to get these respective images as visualizations for these weights. And what's funny about this is if you're looking at this image here, you see that this kind of looks like a car, right? So in other words, what we have done here is, I didn't go into the math how we have optimized this, but in practice, what we have done here is we're trying to find, on average, what is the most common feature, what's the most commonality in our in our data set, such that the score functions become high. And in practice, if we're doing this with an L2, for instance, you know that the optimum of an L2 optimization is always going to be the mean. So what we're getting here is kind of like a mean optimization. So this W here will essentially converge to the mean or the average image of the cars. This one will average to the average of the horse. And for every other class, it's the same thing. So what's interesting is because the CIFAR data set is so simple, based on this very simple optimization where we're kind of getting this average output, we can actually recognize some of the shapes, which kind of makes sense because that's what you would expect if you're feeding these images here as input. Now, for some images here, or for some of these visualizations, it's kind of interesting. So if you're taking the horse, for instance, if you're looking very closely, we're seeing the horse here, right, in the middle, and we're seeing that this horse has kind of two heads. And the reason why it has two heads is because in our data, we're going to have some horses that have the head on the left-hand side, and we're going to have some horses that are on the right-hand side. And what we see here is that the head of the horse on the left-hand side is a little bit more pronounced than the one on the right-hand side. Well, why is that? Because we simply have more horses in the data set that look to the left than to the right. The same thing counts for the car. If we're taking kind of this car here, we can kind of infer that a lot of cars in this data set have kind of a reddish, maybe bluish color tone, right? And this is the result. What we're getting here is an output. So for these simple images, it's actually kind of interesting. If you're training a linear score function here, you're actually going to get some pretty reasonable results for this classifier on CIFAR 10. Why? Because it's such a simple data set. The objects are relatively centered in the image. And because of that, you actually can kind of see these patterns in the respective W visualizations. So on CIFAR 10, this works. But now if you're taking a more complicated data set, is, for instance, ImageNet. So ImageNet has over, I think it's total like 12 to 14 million images or something like this, and it actually has 1,000 different classes. It's much, much more diverse in terms of the data that it actually has. And now if we are optimizing for our W weights here, the visualizations look something like this. And you can already see that here it's actually a lot more complicated to spot any patterns. And it's not only that there's like a lot more classes and a lot more images in the data set, it's also that the images are more complicated, meaning that the objects that are shown in the image are not always specifically and precisely in the center. And because of that, like you're going to get some more, well, unparsable results. So what do we learn here? Well, I don't have the exact numbers here, like how high you can tune a linear score function here on CIFAR 10, but you can expect that this one here does actually something reasonable. On the other hand, if you do something like this here, on ImageNet, a more complicated data set, it's gonna get a little bit more complicated. And if you're doing this more conceptually with these linear score functions, at some point you will see that a linear separation is just not possible anymore. So for instance, if you have a classification problem that looks like this one, right? You can have a hyperplane here in the middle that works out. But if we're having something that looks like this, and we would like to have, more nonlinearities, that's the term I'm going to use more and more, where it's not possible to have a linear separator between the two classes here, then we have to do something better than a linear score function. And this is kind of the high-level concept we're going to talk about right now. How do we introduce these nonlinearities? Well, so how can we make it better? how can we make our linear regression better? Well, the high-level idea is that, and this counts for most of the machine learning problems, generally speaking, the high-level idea is we want to have a model, and a model should be a function that is complex enough to represent the training set. Let's ignore for now generalization. Let's just talk about how can we approximate the distribution of the data in the training set. That's the whole point of machine learning, right? So we're having a training set and we want to fit a certain function, i.e. our model. We want to fit this to our data, and then eventually we hope that it generalizes. But the big point is, what is that function going to look like? And so far we have seen two different types of these functions. One of them was our linear regressor, and one of them was our logistic regression. And now the whole point of this lecture is going to be, how can we make this model more powerful? How can we make it represent more complicated distributions of data? And then later on, we're going to talk about how we're going to find this model, or how we find its model parameters. So the simplest thing, what we can do here is we could think about, well, we have a W matrix, right, of these weights of our linear model. So why don't we just go ahead and multiply these weights with another set of weights, right? So now we have a W and a W2. So what we could do here is we could say, well, this is our first function, these are our outputs, and we're multiplying them again with another matrix. Okay, so we're going to get something like this. So we have X here is our input, let's say it's our image or whatever features we have in our data points. We're multiplying first with W, and then we're going to multiply them with W2, and then we're going to get F hat as our score as an output. Okay, so this sounds pretty good, and in principle you can add more and more W's here. But the little problem that you're going to have here is, like, these two matrices, if we're multiplying them together, it's still a linear problem, because I can still go ahead and multiply these two matrices. Now I have W times W. I'm going to get W hat here, and I have still one matrix that is multiplied with X. And this is the core problem why you cannot simply stack two linear models together, because if you stack them together, they're still going to be linear. And no matter how many times I multiply a different set of matrices here, at test time, once these parameters are being optimized, these parameters, they always going to be a simple matrix. So it's always going to be a linear regression. So the only difference what I'm doing here when I'm adding like more parameters here, I'm changing the way the optimization will work, right? So basically I'm adding more parameters. My problem will be under constrained. I will eventually use the normal equation to regularize it out again. And I will optimize for it. But the model in itself still stays linear. So that doesn't address this problem, right? Remember what I've done in the previous slide here? Here I want to have something like this. I want to have a more powerful model where I can also separate nonlinearities in my data. And that's exactly what we're going to do right now. So what we do is, instead of just multiplying two matrices together, we're adding nonlinearities in between. And that's what we're going to do. And this is exactly what a neural network is. It's actually very straightforward. So we're going to start with a linear score function that we had, right? So we have F is equal to W times X. And now what we do is we want to nest the parameters in our neural network, right? So if I have a two-layer neural network, what I want to do is I want to say, I take the W1, this is my first set of weights, times X, right? This is nothing else but this linear model that we had in our linear regression before. And then I multiply them with W2. But instead of just multiplying it with W2, I'm adding a nonlinearity here. And this nonlinearity is something that is not just a simple matrix multiply, but it's something that has a nonlinearity in the function. In a very simple, the simplest way to do that is to using a maximum function here, right? So I say, well, take the output of W1 times X. If it's smaller than 0, clamp it to 0, and then multiply it with W2. And it's a very simple nonlinearity, right? In itself, it's not very powerful, but what I can do now is I can actually go ahead and stack multiple layers together, right? So I can go ahead and have a third layer. So I have W1, W2, W3. I have a fourth layer, and I have W1, W2, W3, W4, and I have a fifth layer, and so on. And I can do this up to 100 of layers. And this is in practice what people are doing when they talk about neural networks. So what they have is they have different layers. And layers in practice means they have these weights that are associated with one specific layer. And at the end of each layer, they're going to have a nonlinearity, which is in this case a maximum function. Or in this case, you saw it's a tanh function or a sigmoid function. There could be multiple choices for these different nonlinearities, but the point is you need one after every layer. So every time you're applying a matrix multiply, you afterwards have to apply a nonlinearity, because what we have learned in the previous slide was if we didn't do that, the two matrices would just be multiplied together and they would become linear again. So the different layers here wouldn't make a big difference. And this is neural networks, right? This is the whole point of neural networks. And this took people actually quite a while. Now, this is the same image that I've shown you at the very beginning, and people have figured this out over time. So this multi-layer perceptron was essentially introduced in the 80s, and then people figured out how to train them eventually with certain methods. We're going to talk about these ones, how we optimize these larger models now, and then eventually this is what we would call modern deep learning, where we can now stack many of these layers together. We pick the right layers, we pick the right nonlinearities in between the layers, and then we can also optimize them, and we can figure out how to train very powerful networks. Okay, so let's go back to our problem what we had before, and I want to make this a little bit more clear because I rushed a little bit over all of these things right now. So we started with our standard regression, right? This was a linear model. We have a linear separator. That's all we could do there. And now what we want to do is we want to have neural networks that separate out, for instance, that finding decision boundaries between these two types of images. So here we have Jon Snow on the top, and we have on the bottom a bunch of White Walkers. And we would like to figure out how can we learn this classifier? Well, and this is exactly what we have done right now. We had these nonlinear score functions. Basically, we're stacking multiple layers here together. We have here W1, right, maximum, then times W2, W3, W4, and so on, and we're stacking all of these together. So these are our nonlinearities. And now what we're gonna get is, we can do the same thing what we have done on CIFAR, for instance, right? So on CIFAR, we're gonna here see, these are the respective scores that we're getting here as output. And of course, we don't just have a single layer right now, but in fact, what we're getting now is we can have multiple layers right now. So this is, for instance, a visualization of the very first layer that tells us how do we get different activations for each of these sets of weights, given the respective input. And this is what neural networks are. So here, what we have done right now, we have gone from a one-layer neural network to a two-layer neural network, right? So if we're going through this again, we have here for one layer neural network, this is what the spoiler was in the previous lecture, where we had this logistic regression. So we're having here a linear function in between, w times x. We have f is our output, these are our scores respectively. And here, now what we have done is we have now a two-layer neural network. Now we have this nonlinearity in between with our maximum function. Times W2. And then we're getting F as a respective output after having a set of W1s and a set of W2s. Now, I want to make this concrete again for the image classification. Let's in this case assume we have an image that is 128 times 128. So our input dimensionality of X is 16,384. It's about 16K dimensional problem that we're dealing with. And our output here, our F, is 10-dimensional. Why? Because we have a classification problem, and if this is done, for instance, on CIFAR, it's CIFAR 10, meaning that it has 10 different classes in the ground truth. Then we need 10 different scores for each image's output, and then we'll be doing whatever is the largest one or the highest score at the end. This is what we're going to choose as our correct class and assign the label accordingly in our predictions. Right? Okay, and then the next thing that we're going to do is, well, now we're going to go ahead and say, now we have 128 times 128. We're having now this two-layer network. We first multiply it with W1. Then we're going to get to a hidden layer. And this hidden layer, let's say, has a dimension of, 1,000. Then we're multiplying this one with W2. And then we're going to get to our dimensionality of the output scores, which is 10-dimensional again, which is what F is. Right? Okay, so a couple of things why before we're talking about structure here. One thing is important, mathematically speaking, that you always understand the dimensionality here. So what is the dimensionality of W here, right? So W is a matrix. X is actually a vector. This is a little bit confusing because this is actually an image. So an image is a two-dimensional thing, right? But in practice, imagine it that this was a linearized version of an image and we're just multiplying it with W, right? And what that means is, well, our W here has a dimensionality of 16,000 times 10, because that's what the output is respectively, right? So each row of W has to be multiplied with this one here, right? And then we're going to get one score output. We're going to get one score function for each of these outputs. Now, if you imagine it, basically, in W, if you take the first row will correspond to the first score of the first class. So the first class is equal to the first row in W, right? So these two things correspond to each other, and then they give you a kind of a response function that tells you, oh, if I feed in this image, how high is my score respectively for that specific image, right? And for that specific class. And this is the thing what's important, right? Now we have the mathematical framework of saying, well, W times X gives us our scores, and now we can simply start stacking. And this is what we're doing here. So if we're going here again, we have here W1 times X. So W1 is this one here. W1 now has a dimensionality of 16,000 times 1,000, because 1,000 is the output of this intermediary, let's call it, it's a hidden layer, and the output of the hidden layer is with 1,000. Then we're multiplying it with W2, and W2 has a dimensionality of 1,000 times 10, and then we're going to get to our 10-dimensional output. Okay, and before we're going into more detail right now, how do the W's look like? How do the activation functions or the score functions, these linearities look like? Now I want to talk a little bit about the structure. And what people typically do is they don't write all these dimensionalities out. Maybe they should, but at some point it becomes very tedious, because it turns out if you have not two of these here, but hundreds, you need to introduce a little bit of structure. And this is a couple of reasons. So first of all, just for educational purpose, well, it's very easy to do it this way, because I can just say, well, this is my input layer, this is my hidden layer, and this is my output layer. And now I'm going to draw a bunch of arrows here, and these arrows are nothing else but the respective weights in these matrices in W1, W2, and so on, right? And this is abstracting it away. So we have here our input layer, we have our hidden layer, and our output layer, and these connections here, they correspond to the matrices, right? So W1 is these edges here, and W2 are these edges here. The input layer has a dimension of 16,000. This is this one here. The hidden layer is this layer here. And the output layer is that layer here, right? Okay, so the reason why the structure is quite useful, because when you're thinking about it and you have very deep layers, this becomes at some point very, very complicated, right? So if you have a three-dimensional input here, x1, x2, x3, then this looks something like this here. In this case, you see we have three sets of W's. We have W0, W1, and W2. And then we're going to get here the score functions as an output at the end. And this is actually quite an important slide. The reason why I like that slide here is mathematically, it helps you to think about this stuff as indices. Why? Well, so this one here is, the question is always, how many indices do we have? Well, for W, we have three sets of W's here. And we have one set of X's, we have one set of outputs at the end. And we need to know how we index them. So now we're going to talk already about layers, and we're going to talk about different neurons in different layers, right? So if I'm going to talk about a layer, then I mean this one here. This is layer 1, this is layer 2, and this is layer 3. So we have three different layers here. All of these have different weights. And the first index of this W is 0. That's the 0th layer, first layer, and second layer. Now, we have another index, which 0, 0 means 0th layer and 0th neuron. This one is the first neuron, second neuron, third neuron. Same thing. zeroth neuron, first neuron, second neuron, and here we have only one neuron, right? So the two indices on the W's tell you which layer and which neuron. And then within one neuron, you also have several weights. So a neuron is not just a scalar, but in fact, a neuron does a certain thing. A neuron does a matrix, does essentially a dot product. And the dot product means it takes all of these features as input. So 1, 2, 3. So it has three-dimensional inputs. And it has basically, this one is a three-dimensional dot product, what you're doing here, right? Because it has 3 dimensions input, it has 3 features here, and it needs 3 weights to do this multiplication. Okay, so the number of inputs to a neuron tells you how many weights that the respective neuron has, right? In this case, this W has 3, this one is 3, this one is 3, this one is 3. And a spoiler alert, all of the neurons in one layer, they also should have the same dimensionality. That's typically how we do it. And here we have 3 input. That means all of these weights here have, all of these neurons have 3 weights respectively for the matrix multiplication. And here it's the same thing, except we had here 4 neurons in the previous layer. That means that this one actually, this X here is this one here. It's the output of this one. It's 1, 2, 3, 4. So this is a 4-dimensional dot product. And spoiler, this is a 3-dimensional dot product because I have 3 inputs here, right? Okay, so there's a little bit of a detail that I sometimes swept a bit on the rug. You see there's a lot of B's here. These B's are these biases. This is the same bias what we had already in the linear regression. It's just a constant factor per neuron. Why do we need it? Well, you need a constant offset respectively to make the neurons powerful enough to fit the respective and approximate the respective function. Okay. What's also important when you're talking about these biases, B has 2 indices. So 0, 0 means there's 2 indices, and this is a scalar that is added on top after you did this dot product here. So this is a scalar, this is a scalar, this is a scalar, this is a scalar, and you have 2 indices here. First one tells you the layer, second one tells you the neuron, right? This is a scalar, this one is a vector, and this one is also a vector, right? And doing a whole layer together is matrix vector multiplication plus a vector of biases. And doing the whole thing then together is successively applying matrix multiply plus bias, matrix multiply plus bias, and so on. And of course, we're going to have some nonlinearities in between. That's part of this f function here. And we're going to talk about this. Okay, but back to the original thing, what I wanted to say is it's very important to keep this structure because it's going to simplify the whole mathematical stuff. Later on, when you're going to implement this or when you're going to use any deep learning frameworks, you're going to also have to figure out how to abstract it away because otherwise it gets a little bit complicated. And you can see this already here. This is a neural network that has 3 hidden layers, right? That means we're going to have a lot of different connections here. And you can imagine if this is suddenly hundreds of neurons per layer and hundreds of layers, then this is impossible to draw anymore. Then you need to go ahead and actually abstract it away. This is why this structure is in fact so important. Okay, so what do we know now? Well, we know what we do need is we need layers. Each layer is a linear part and a nonlinear part. And then we just stack them together and eventually we're going to get an output of our score function. And the reason why we're doing it is very simple because now we want to have a model that is nonlinear globally speaking. We're introducing these nonlinearities. And again, we want to fit this model to our training data from the train set. We want to approximate the data distribution of our train set to the best of our ability. And then we hope it's generalizing. It's always the very same machine learning concept that we want to apply here. And we want to learn these weights based on optimization. We're going to talk about later of these ones. And we want to stack many of these layers to make our model complex enough to represent complicated distributions. Okay, so the one thing we haven't talked a lot about is these nonlinearities. And we're going to talk about these ones later on in a little bit more detail, but I wanted to give you a high-level overview. And this is really funny in a sense because it took people, or by people I mean researchers, it took them actually quite a while to figure out what are good activation functions. And we're typically going to call them activation functions for the reason is because we're going to have neurons, right? There's a matrix vector multiplication there. And then you're going to have this activation function that tells us what is the output of the score function respectively. Okay, so these are a bunch of common activation functions that are being used. These are nonlinearities that people use in neural networks for various different purposes. Some of them we have already seen. So the sigmoid function we have seen in the last lecture in the context of the logistic regression already. And this was the spoiler because we had this one layer neural network where we had a linear part and one nonlinear part. This was the logistic regression. And the idea there was that, well, the sigmoid function, it squashes the values between 0 and 1. So it kind of interprets it as a set of probabilities. And it's zero-centered. And this is typically something you can use in the output, in the last layer. It turns out people actually, when they develop the neural network, sigmoids are very popular choices, also for the hidden layers in between. But we will later see the implications of how well or how not well this works respectively. 10H, we've already seen that one. That's also a very popular function. It looks kind of like the sigmoid function, a little different, except it's a little bit more flat here, right, on the outside. It doesn't have such a smooth transition here, but on the high level, it's very similar. However, the range of the outputs is going to be between -1 and +1. This is a big difference between the 10H. And this is kind of important when you're designing neural networks, that you expect the score functions at the very end, for instance, to give you right outputs, or even in between, right? This is very important that these value ranges are being considered. We've also seen this maximum function. These maximum functions are called ReLUs, rectified linear units. And the idea behind that is that you simply have a maximum function. So everything that is negative is going to be clamped away, and everything positive is just kept as it is in the input. And little spoiler here too, it turns out that these very simple activation functions perform actually quite well. This is what modern neural networks are mostly ReLU based. And so it turns out that it's actually quite advantageous if you adding the complexity of these nonlinearities through many, many layers rather than making one layer more complicated. And there's a couple of different variations. There's the leaky ReLU that is saying like, well, don't clamp it all the way to 0, but have 0.1 times x and x here. That looks like this, right? So you have two different slopes here in this function. Parametric ReLUs are interesting. So now you're learning this parameter here as well. So this alpha here is now becoming a learnable parameters. There's things like max out. That's very, well, wouldn't say it's super common, but it's a very, it was theoretically an obvious choice. And there's ELU functions, where you have functions like these ones here, and so on. In fact, there's actually a lot of different activation functions possible for neural networks. And throughout the history of the last 20, 30, 40 years, people have tried a bunch of them. And they have not just tried them in the context of neural networks. It's always the same question, basically. Is like, you have this machine learning concept, you have a training set, and you want to approximate the distribution of your training set to the best of the ability. And the way you want to do this is you want to introduce these complicated models, and now you have to figure out how to introduce these nonlinearities. It's always the same question there. And yeah, and we're going to talk about which choices are going to be good in which case in a little bit. But we have to get a little bit more background first so we can make good decisions here when and which of these activations are actually going to be appropriate. Okay, so quick summary. So neural networks is a stacking of these linear functions. Now, the point is what I wanted to make is we need these activations because if we simply concatenate the W's here together, like here, it sounds a lot cheaper and looks pretty good. But if you're multiplying two matrices, you're just going to get yet another matrix. And as long as this is another matrix, the model in itself stays linear and you can just summarize them together. And this is a very big problem because then you would still have a linear model, right? But you want to have the nonlinearities, to have nonlinear decision boundaries, to have more complex functions that you can represent with neural network. And this is the whole reason why we need these activations, why we need these nonlinearities. Why do we organize neural networks in layers? Well, obviously we want to have this abstraction, and there's going to come a few more things in the next lectures. It turns out from a computational perspective, it also makes sense to organize them into layers. Why? Well, it turns out that a cooperation that we need for neural networks is a matrix multiplication. So if we are introducing each layer as a matrix vector multiply, it turns out we can actually write an abstraction. Like we have an API that says, oh, we have a layer that looks like that, we have the layer that looks like that, then we have these layer templates. And we can actually abstract away the implementations and then map super fast high parallel code that runs on a GPU in parallel, on a graphics card in parallel. We can map them into deep learning frameworks, and we'll later see this is exactly what the deep learning frameworks are going to do. So there's things like TensorFlow, PyTorch, and so on. So these folks who created these frameworks, and by the way, these frameworks were instrumental actually to make this stuff happen, because we need a lot of these layers, we need a lot of compute, we need to make this very, very abstractable. Otherwise, you can't really practically handle large complexity of the neural networks. Right? So this is why we organize them into layers, and conceptually then it makes also sense how we optimize the parameters. We will see that we need methods how to compute gradients through that. From these gradients, we're then going to compute gradient updates. These gradient updates, they're going to tell us how we need to modify the weights when we're fitting it to the training set, and then we have to figure out how to do the training more efficiently. Okay, so I wanted to do a very, very quick comparison. Maybe comparison is actually the right word. I wanted to set this quickly in the relation when we talk about neural networks, artificial neural networks, in the context of computer science, in the context of AI. I wanted to set this briefly in the context of biological neurons. So biological neurons, they look something like this. And I'm no neuroscience guy. I have very little intuition how the biochemical processes in cells, and not to mention about the brain, actually work in practice. But this is roughly how a neuron looks like, right? This is like a cell in the brain, right? And what you're going to have there is you have a nucleus, we have a cell body here, we have these dendrites, and the core idea is that these impulses, they are carried towards the cell body, and then they have axons, and these axons, they spread out, they spread away from the cell body, and they forward the impulses to the next basic cells, to other neurons. And then this is kind of what an actual neural network in the brain looks like. Now, when we're talking about this and trying to compare the two, a lot of people might say, well, it's kind of similar, right? So we're having these inputs, these are electric pulses, like in the brain. This is literally how it works. We have these electric pulses, they're being modified in a certain way, so they're being combined from different other inputs here. They're somewhat being modified with a function. They're being carried forward, and then they're being forwarded to the next neurons, and they do the same thing again, and so on. So the idea basically is, well, okay, what we just learned here is this is kind of similar, right? So these artificial neural networks, or these artificial neurons, we have a cell body. This is our linear part, right? We have F is our activation function in the output. So in a sense, we're mapping what the biological neurons do, and we're trying to have a mathematical model for a neuron. So we're kind of imitating what the brain, or what like neurons in the brain are doing. So there's a couple of caveats. So in principle, it is true that when people develop these kind of things, they were inspired by the brain, which we do all the time, right? For instance, in humanity, when we developed like airplanes, we were inspired by birds. That's not a new thing. But that doesn't mean that whatever we're going to come up with is an airplane is not flying like a bird. They are flying differently. They are not like using their wings. They are not like moving their wings at all, actually, right? So it's going to be very different. And in practice, this is very similar here too. So it turns out there's a lot of key differences. And again, I'm not a neuroscientist. I'm not an expert at all here. But I just wanted to say like the complexity, how these functions look like, are very different than the functions, what these activation functions are going to look like. And the cells itself have a very different behavior than these linear parts that we have as well. And this is very important to understand, that while we inspired here, we don't do the same thing, right? I'm not going to go into more details how the actual biological cells of a neuron work, but I wanted to make sure that what we are using here in artificial neural networks, they are very simplified mathematical models, how we can combine signals from the inputs here. We're taking these signals, we're forwarding to the next neuron, And the whole point is still that we have a complicated function as a whole, or a function that can represent a complex data set, and we can fit this to this data set, and this is then our neural network that we are training. And I do understand that, we're gonna have a lot of people in the media or so, they're gonna claim, well, artificial neurons are now doing what brains are doing. They're not doing that, by no means at all. So I mentioned this, that they're definitely inspired by the brain, but they're not even close to the complexity. It's very easy to simplify that. And one of the important things as part of this course that I want everybody to remember here is that what we are doing is not doing the same thing what a real brain is doing. It's very different. And it's great to have inspiration from nature, but it's just not the same thing. And even when you're talking about the very recent headlines, what we have seen, right? We have things seen like large language models, ChatGPT, GPT-4, stuff like that. That is just not what the brain is doing. We're going to talk about what these models are going to do. For most of these things, we have very simple explanations why they behave in certain ways. We have a good understanding of how their training processes work. We also have a good understanding why you can scale them so well and why they can achieve very impressive results. But by no means, just because something achieves impressive results, doesn't mean that, we have suddenly replicated human intelligence at any level, right? There are certain things we're going to realize that computers are pretty good at. Neural networks are pretty good at certain things, but that doesn't mean that, they have suddenly imitated the brain to a level where we have human level intelligence. We are far away from that, even today. Even there's a lot of clickbait headlines all the time. I hope everybody who comes out of this course appreciates that and knows how to actually interpret these kind of clickbaity headlines. Okay, but back to actual neural networks, right? I talked a little bit about this one. I think this is still a very important slide here. Whenever you're lost in terms of how many parameters do you have and stuff like this, think about this slide here because it tells you exactly what the dimensionalities have to be, right? We have here our x, three-dimensional input, means out of each input, we're feeding it into each of the neurons of the next layer. Then what we do is we have a set of weights for each neuron. The number of weights here in this weight matrix is equal to the number of input features. So this one has 4. It's a three-dimensional dot product because we have 3 inputs. We have 1 bias, so we have in total 4 weights for this neuron, 4 weights for this neuron, 4 weights for that neuron, 4 weights for that neuron, and so on, right? And the same thing for the next layers. And this is something I would really like you to encourage to think about it from a pure mathematical concept, right? It's very straightforward. The F functions here are activations. We can have all kinds of different activations as we have just seen, and we're going to talk about which ones are the right ones at the end. Okay, so if we are summarizing our neural network right now, what do we do? And I think I'm repeating this many, many times, but I want to make sure that everybody gets it. So if you're given having a training data set, right? So with a data set, we have ground truth pairs. Ground truth pairs means for a certain given input x could be an image. We can have a y, which is our label. In this case, could be an image label, like a class label, like dog, cat, and so on. These are our y's. And what we would like to do now is we would like to figure out how can we fit this neural network, how can we fit this complicated function that we have just defined such that it best explains our training data set, meaning that it makes the same predictions as if the ground truth would do it, right? And mathematically speaking, this leads to an optimization. So we have to find the optimal weights here. And weights and biases, I'm including them both here in these W's, right? Using stochastic gradient descent such that the function is minimized. So the optimizer we're going to use later is SGD. We're going to talk about this one, how this works. It's a gradient-based optimizer, and we want to minimize that function. There's one little caveat. I'm a little bit inconsistent here with the notation. When I talk about weights of a neural network, sometimes I mean weights plus biases. Actually, most of the time I mean weights plus biases. So biases are parts of the weights, but sometimes my notation is a little bit inconsistent because the biases, they're not part of this dot product, right? It's just added afterwards after you did the dot product. You still need them, but they're practically part of the weights, but they're not always part of the W. So that's why I have to apologize for that at some point. I need to fix these slides and make sure this is more consistent, but it's actually not so straightforward from a conversational standpoint. But I hope you get the point, right? So there's the W weights that are part of this dot product. Again, if you're going back here, there's these W's, there's these B's. And both of them together form the actual weights of the neural network. And sometimes W refers to both, and sometimes W refers to one. Apologize for that one. Okay, but what do we want to do? Now in this part of this optimization, I'm sure everybody has heard about gradient descent at some point, right? We've already seen this in high school. The whole point right now is how do we make this fitting process work out for us, right? So when we have a very, very large training set and a very, very large neural network, how can we make this fitting process work out? And how can we do this optimization? So what we have to do here is we have to figure out how to compute gradients. We have to make sure we take these gradients that we've just computed in order to update our network weights. We iterate, and eventually, hopefully, we fit the training set and approximate its distribution. And once we have done that, we hope that it generalizes to unseen data that we haven't seen before. And there's a couple of terms on this slide that will guide the next few lectures. We're going to talk about computing gradients. We're going to talk about backpropagation. Backpropagation is a way to do that. There's a batch mode thing. There's something we call batches, how we compute gradients. We don't compute them on the entire data at once. We compute them in parts. We iterate many, many times over the training set. There's a thing called SGD. That's what I mentioned. This is stochastic gradient descent. This is the optimizer of choice that we're going to use once we have computed the respective gradients. Okay. If you have not heard these terms, no problem at all. This is the point why we have that lecture. We're going to go into it step by step. But I want you to get the big picture first, and then we're going to pick one by one and make sure that everybody understands what's going on there respectively. Okay, so the one thing, what I mentioned already a couple of times, is that these functions and these networks, they can be quite complicated, meaning we have a lot of parameters. And you can imagine if you have a very complicated function, it's actually not so straightforward to compute these gradients. Like I have a single training sample, I feed this training sample as input, and I want to make sure how do I have to update my weights such that they fit better and approximate better what the respective label gives me for this ground truth pair. And to do that, you have to compute the gradients. You have to figure out how do I need to update the parameter weights. And the way we're doing this in neural network lands is via computational graphs. And this is also a reason why we organized our neural networks into layers and the specific structure what we have. But I wanted to come with a very generic introduction first, because some people might recognize computational graphs are heavily being used when it comes to auto and symbolic differentiation methods, right? So just from a pure math standpoint, how do we get computers to compute derivatives, basically? This is what computational graphs are doing. Okay, so computational graphs is a directional graph. So there's an input and an output direction. Operations are typically represented in the nodes. So every node does a certain operation. In practice, these operations are certain matrix operations. And then vertex nodes are variables operators like plus, minus, multiplication, division, logarithm, exponent, stuff like that. And then the directional edges show the flow between those nodes, between those vertices, right? So let's just start with an example. So we're going to make this very, very simple. We're going to start with a dead simple function. We're going to explain the notation around it. And then eventually we're going to go into making sure this fits to our structure that we have in neural networks. So eventually these computational graphs, they will be mapped to our neural networks, and then we can use certain algorithms like backpropagation in order to compute gradients. That's the whole point why we're doing this now. Okay, let's start with a simple computational graph. Okay, let's say we have a simple function. Let's say we have a function f. F takes as input x, y, and z. And what we want to do is we want to say, well, x is first added to y, and then the result of this one is multiplied by z. So x plus y times z. This is what we want to now represent as a computational graph. Well, how do we do this? Well, we just say, well, X is an input, Y is an input. These are two nodes. This is our flow here. These are our edges. And here we're having a summation. We just say, well, add X plus Y. This is how we represent our graph. So this is a node, this is a node, this is a node. We have two edges for now. So this is the inner part here. And then what we do is we get Z as input, and the result of this one here, we're multiplying with Z, and then we get the respective output here at the end of the day, right? And computational graph is not something that is just specifically developed for neural network. That's something that in computer science, in many other areas, people have been using over and over again. And you should have seen many of these things, right? For instance, when you're talking about compilers, when compilers are compiling code, then you have a computational graph, and the compiler is trying to optimize the nodes, right? It's trying to simplify the graph in a certain way to save some compute, to be more efficient, and so on. And we're doing the same thing here. We're having this function, we mapped it to our computational graph. Now, assuming we want to evaluate our function f, and we want to figure out what is the respective output. Well, assuming we set these variables, these inputs here, x, y, and z, to certain values. So let's say we initialize this with x is equal to 1, y is equal to -3, and z is equal to 4. Right? So this is just our input. So I assume this is not so complicated, right? So we're just going to set these ones here. Well, we have our edges as our flow, right? So they forward all this stuff here. So now we first compute this intermediate here. So 1 plus -3 is this intermediate -2. And then we're multiplying -2 times 4, and we're getting a respective output, right? Okay, so why are we doing this? Well, as I said, later we want to map this to neural networks. And we have already one part of the neural network in a sense. We have actually done what we call a forward pass. So forward pass means give me the nodes. And now what we want to do is we want to just give some input at the beginning of this graph. We're feeding some input in, and then we just forward evaluate the graph. Later, this is going to be layer by layer. Same thing, this would be one layer, and then this would be the second layer. It's not quite like a neural network because you can have these skip connections. Some neural networks have that too, though. So this is kind of a special neural network, right? It skips one thing here. But the idea of the forward pass is there's no optimization right now. This is only give me input, do the math operations in our graph, and then compute the respective output. This is what we call a forward pass. And you might guess there's this thing called a backward pass later on. We'll talk about this in a second. Okay, but what we need to do is, why do we do this? Well, why discussing these compute graphs? Well, the neural networks, they have really complicated architectures. And we want to map them in simplifying to compute graphs. I hinted a couple of things already, right? A lot of these things are matrix operations. And each of these nodes that we have in our compute graph, we can actually map very efficiently to graphics cards, for instance, to do the math and do the heavy lifting for us. So it's a very, very nice abstraction. And we will also see that these compute graphs, they can be then used to compute the gradients. This is why we have this backward pass. That's why we do back propagation later. We can also compute the gradients in like this node by node fashion. This is why we have compute graphs here. Okay, so what's the similarity between the compute graph and the neural networks? Well, a neural network can be represented as a compute graph. It has nodes, it has these operations, it has the edges, that is the flow, it's directional, and it's organized into layers. What I've been saying is compute graphs can represent neural networks and vice versa, right? Okay. Why do we do this? Well, now we have these complicated compute graphs. This is one example here. Again, we have here the inputs, we have the immediate outputs, and so on. And here we see still the math, but later on you're going to see stuff like this one, right? So from a set of neurons, you go to a structured pipeline. And this is, again, very important when we're talking about deep learning frameworks. When we're mapping the operations to the GPU, we're going to have these computational graphs, and we're just going to have this abstract drawing here, this visualization that visualizes our neural network, and we don't have to write every little math detail down. So far, when we're doing it right now, we might have to write the math detail down for a bit because I want you to understand what every node is going to do, because this is very important for the high-level understanding later on. Okay. We're going to see neural networks for many different things. The computation of neural networks has further meanings. The multiplication of W and X encodes certain input information, so we're going to get these intermediate features between those. And the activation function that has a certain idea of selecting these key features and propagating them accordingly down in our compute graph. And eventually we're going to have some output here. And you're going to see there's already a couple of notations. Some of them we know already. So relos we've already heard, right? These are our activation functions, conf, pool, and fc. We will see soon. But you can already see like how we can then abstract from these original functions to high-level structures and make the thing possible. Here's another example. One thing we're going to learn is convolutional neural networks, right? So we're then going to add more and more structures to these layers such that we force them to do a certain way of learning, right? And convolutional neural network is one of the things we're going to talk about. These are special neural networks, so to say. They extract useful features with shared weights then. And then it becomes a part of like how to optimize them. Yeah, neural networks, specifically convolutional neural networks, is a thing that we will see very commonly for feature extraction in image classification, in image segmentation, and so on. Okay, so we've learned a little bit more. We have basically learned now, well, machine learning basics, talked about a lot of things there. We have learned computational graphs. We know how to stack and organize layers of neural networks. The one thing we have not learned so far is the loss functions too much, right? So in other words, well, we talked a little bit about them, right? So we've talked about the inputs here. We have our neural networks. They're going to give us some outputs, and this output are these respective scores. This is why I'm talking about score functions all the time. Now we have to measure, in a sense, like how close are these outputs to our targets? Like, are these reasonably close, right? So we need a way to describe how close the network's outputs, the predictions, are to the respective targets that we have in our ground truth data. And this is the thing what we have in our loss function. And what we would like to do is here, well, it's very simple, right? We just run a training sample throughout a neural network. And then we calculate a distance between the prediction and what the output should be. And if we have a large distance, we have a bad prediction. And if we have a small distance, we have a good prediction. That's all what we want to do, right? And some of these loss functions we have already seen, right? So binary cross entropy we have seen in the last lecture. We've talked about the L2 loss, the mean squared loss function, and so on. But this is going to be pretty important right now because these loss functions will determine how we have to do our optimization in these neural networks. So a loss function here is nothing else but a measure the goodness of the prediction or equivalently the network's performance. In other words, we would like to make sure that the predictions the network does is matching with all our annotations in our training data. And intuitively, a large loss should indicate we have bad predictions. Performance needs to be improved by training the model further, by running our optimization. We'll see how that works. And the choice of a loss function depends on the concrete problem also, right? We've seen like linear regression has a different loss function than logistic regression, right? This was what we have done in the last lecture. But even for regression, you're going to have different losses, right? We had L1 loss, we have an MSE loss. They all have different results. And if you're looking at what are the parameters of my loss function is always, this is the prediction y hat, y is our label, and theta is going to be the respective part of our network that we need to optimize for. Theta are the network weights, right? Okay, so here in our L1 loss, again, we're summing over all of our training samples. This is O1 over n. These are the respective ground truth labels. This is the predictions. And we want to minimize that such that it's clear. So where are the thetas here? Well, the thetas are part of this y hat here, right? MSE loss, same thing. It's the sum of squares. This is the sum of L1 terms. And these are giving different optimization results. I mentioned this before, right? Like very importantly, like from optimization, from math classes, you will know L1 losses, the median is the optimum here, and here the mean is the optimum. Talked about this one now a couple of times, the binary cross entropy loss. Binary cross entropy loss has the negative term and the positive term of the positive samples, the negative terms, and the network predicts the probability of the input belonging to the right class, right? So we have an image here, we want to classify it as yes or no. We're going to get a score, and the score is interpreted as a probability that we can then use to make a certain classification. Okay, we can then see the cross entropy. This is the general case of the binary cross entropy. We will see now instead of having one class, we're going to have multiple classes, all right? So here it was one class, second class. And now what we're going to do is we're going to sum here over all the classes. And then we sum over all classes here, and we sum over all training samples. Only one of these terms will be non-zero. There will be some normalization cases later on we're going to add there. This is the cross entropy. These are what we call loss functions. Yeah, so more generally, this is the notation we're going to use. We're going to have our ground truth labels. We're going to have our predictions, y hat. Again, y hat is parameterized by the input plus the parameters of our model. The loss function is then L of y and y hat. Motivation, we minimize the loss to find better predictions. Predictions are generated by the neural networks. Find better predictions, find better neural networks. Okay, yeah, so the way it should work during training, right? So we're making bad predictions at the beginning. We're training here at T of 1, T of 2, T of 3, and so on. And this is a thing that will be very important when we're talking about training times. We will see that when we're optimizing, we're going to get a thing called the training curve. That's the thing we're going to do very often here. We're going to plot our training time here on the y-axis, on the x-axis, and the y-axis we're going to plot our loss function, right? And this is really probably one of the only ways, not the only ways, but probably the most significant way to debug the neural networks actually, because we can see how the training behaves based on this curve, and that can tell us if things are going okay or if we have to change certain things. Well, the next thing would be how to find a better neural network. Well, now what we're going to do is we're going to plot this curve against the model, right? So here on the x-axis we have the parameters theta basically. On the y-axis we have our loss. So loss is, right, like what our function predicts compared to our ground truth labels. It's parameterized by theta here. And what we do now is here we have a set of thetas, and we would like to figure out which here of the thetas, which state of the thetas, or which parameter values of the thetas are the best ones to minimize the loss. That's what we try to care about. Well, and how do we do it? Well, we have a loss, we have a neural network, and the goal is we minimize the loss with respect to theta. Meaning we need an optimization. We're training a compute graph with certain optimization techniques. We've heard about gradient descent, we've heard about SGD. And that's what we're going to do. We're going to run gradient descent here. How do we do that? Well, again, we have our loss, we have y here, our ground truth labels, we have our model here, parameterized by theta, and x is our input. And in the context of neural networks, we use these gradient-based optimizations, meaning we take our initial theta here, we're trying to find the gradient, and we follow this gradient around in order to find the minimum loss value as possible. You can already see it's not so easy, right? It has a bunch of non-local behavior, non-convex behavior. So we have to think about how we deal with those ones as well. And so on. Okay. Yeah, so we get the gradient. This is the gradient here. And if we're doing gradient descent, right, we follow the negative gradient direction, and we're having this function that we optimize. So we just find the argmin, the optimal parameters theta, which is our ideal network parameter weights, such that this loss function here is minimized. This alpha here is the step size of the gradient. In machine learning land, we're going to call it a learning rate, but mathematically speaking, it's just the step size of our gradient. Right. Okay. Yeah, so given the inputs and the targets y, given a one layer neural network with no activations, this whole thing is going to look something like this. So we're going to go quickly through this basic step here. The way this is going to look like is we have f of x parameterized by theta, which is w times x. So our theta is our w right now. This is what I meant later with a notation consistency. So theta is basically w plus b. So when I talk about weights, I mean always all of these weights basically. So these are the network parameters, are the matrix part plus the bias part. Then we have our loss, right? And in this case, we're using an MSE loss, an L2 loss. It's what we get as input is the network parameters y and y hat, and we just sum over all of our training samples. Now, there's no activation in this case, so this is literally our compute graph, is just this little thing here. So note here, here's y I hat, and now what we're going to do is here, y I hat is computed based on this function. So we know that this is yi minus w times xi, which is sum of our training samples. And now we can fit this into our compute graph, right? So what we do now is here, we have x, we have w. Our compute node is doing x times w. It's computing an output value. We have y here as our target, and we have our loss function that computes some sort of difference. And now what we're going to do is we're going to compute gradients with respect to this compute graph. So we're going to have some gradient flow. This flows here back. So how do we optimize these parameters w such that the loss is being minimized for a given set of training samples? Given set of x's and y's basically, right? Okay, and that's what we get here. Now we compute our gradient. This is our gradient here of this L2 loss function that we have just chosen. So it's 2 over n, the sum over all of our training samples. And this gradient here now becomes this function, and then we can update our network parameters after we feed in a couple of things. Okay, so given the inputs x and targets y, we have now done this for our linear model, and for the neural network, when we have a more complicated model, we're going to do exactly the same thing, except that this little compute graph that we have just seen is going to become a little bit more complicated, meaning that we have now many layers, and now we have to do gradient descent for this loss function with respect to theta. We need to backpropagate the gradients from the end to the first layer one. So meaning we start here and we go all the way back to W1 here. Right. Well, how do we do that? Now again, we have a compute graph, which is our multi-layer neural network. Looks something like this, right? So we have here, all I've done here is like take this function here and write it down as a compute graph. So compute graph means x times w1, multiply it, activation maximum, times w2, and so on. And then there's a little bit of stuff omitted here, right? There would be more layers, but at the end of the day, we have our loss function, we compare it to our y, and that's our compute graph. And then what we do is we compute gradients through that whole thing here, and the gradients are computed with respect to w, to all the w's, w2, w1, and so on. Okay, so now the big question is, how do we compute these gradients? And now this is where the compute graphs become quite handy. Now we do a thing called backpropagation. And the idea here is, with backpropagation, we're essentially using the chain rule to compute these gradients, right? So how does it work? Well, how does it work is basically we're just going to go through every node. Every node has a derivative, and backpropagation allows us, leverages this compute graph by using chain rule, by applying recursively from right to left now. We're computing these gradients of these nodes, and then we're computing the gradients respectively. Okay. A little bit of the rationale here before I go into more details. So why do we use gradient descent? It's very easy using compute graphs. And gradient descent turns out to be very scalable with large amount of data and very complicated functions. There's a lot of other methods, such as Newton's method, LBFGS, adaptive moments, conjugate gradient descent, Lemberg-Marquardt, many methods here for optimization. For the neural network land, all of these methods here are somewhat gradient based. For the most parts, we're going to use gradient descent though. Certain variations we're going to discuss about, and that's what we're going to talk about next. In the next lecture, basically, we're going to talk about these optimizations and how to do gradients. And again, since we want to quickly summarize it here, neural networks are compute graphs. The goal is to, for a given train set, find optimal parameters, find optimal weights that best approximate this train set. The optimization is done with gradient-based solvers. And the gradient itself is computed with backpropagation. Now, we haven't talked a lot about gradient descent itself, about the solver, and we haven't talked about the backpropagation also. These are the things we're going to talk about in the next lecture. But it's always the same concept here, what we're going to talk about. It's always we have a model, and we want to fit this model to our train set. And then we hope it's going to generalize. That's the whole concept of machine learning. It's always going to be the same thing. And in the context of neural network land is we have these layers, we have a complicated function. In this complicated function, we need to find gradients for, and we need to optimize it with these gradients. And that's what we're going to do in the next lecture. We're going to talk about backpropagation and optimization. I'd also like small administrative things. I hope so far everything is clear. If there's thing not clear, please ask on Piazza. Check updates on the website on Piazza regarding the exercises. And then today we have already learned how neural networks work. So now we have to just this tiny little thing, we have to figure out how we optimize them. And this is what we're going to do next week. So thanks a lot, everybody, for tuning in. See you next week. Bye-bye.